where we have boundary layer separation. Which can lower the coefficient of drag. So surface roughness is going to be given by a parameter, epsilon. It's going to have a unit of length. So the surface roughness non-dimensional number, or dimensionless number, is given by x over epsilon. It's going to be a ratio of lengths. So x So x is either going to be the local length or the total length. So if we have a plate, it could be a position here, or it could be your total length. The surface roughness is going to be the average height. So if you take a piece of sandpaper and rough up a surface, you can come up with whatever that average height that it is going to be, where the dips and valleys will be in there. So if you look and blue this up, you might have various heights doing like that. So the average height is going to be given by the epsilon. Results in just a pure number, no units on it. Therefore it's a non-dimensional number. So experiments were performed, and in your note packets it is given for a comparison of a smooth sphere compared to a baseball. So again, if we look at a plot, and again if we have Reynolds number, and again if we plot Reynolds number on a semi-log and then regular units on this side ranging from 0.1 to 1.5, ranging from 10 to the 2 out to 10 to the 7. This is going to be a representative scale, but your might do something like this. You have your dip and then going up. So again, your dip is going to be where you turn into turbulent flow. Now, let's say that the solid line is for smooth. And then we can have a dotted line for our rough. So surface roughness, again, is going to be dependent upon Reynolds number. In the beginning part, in the low flow regime, laminar regime, the rough surface is pretty close. But then, before you get to turbulent, you get a different coefficient of drag. And then it actually increases. And then they begin to converge to each other. So again, surface roughness is going to affect the coefficient of drag. Now let's compare and contrast the result within this region. If we're at, let's say that this value is 10 to the 5th, and let's call this value 0.2, this value 0.5. Let's perform our experiment, or let's perform our calculation. So we're going to perform this calculation on a smooth sphere and a rough sphere. Diameter Diameter of the sphere is 0.1 meters. A Reynolds number of 1 times 10 to the 5th. Here would be your particular values. You can look in your note packet for the corresponding graph. A density equal to 1.201 kilograms per meter cubed, and a viscosity of 1.8 times 10 to the negative 5th PA seconds. Let's calculate the force of drag for the smooth sphere. We all should be familiar with this. Coefficient of drag divided by 2 rho v squared a. Coefficient of drag for the smooth sphere, roughly 0.48. Divided by 2, the density is 1.201. The velocity and the area. Again, this is going to be a sphere. You want your frontal profile, so the area is just pi r squared, and our radius is 0.05, giving us an area of 7.85 times 10 to the negative 3rd meter squared. Now we have to calculate our velocity. Again, we're not given the direct velocity, but what we are given is the Reynolds number. And Reynolds number is rho v diameter for a sphere. Where the Reynolds number is 1 times 10 to the 5th. The viscosity is 1.8 times 10 to the negative 5th. The density, 1.201. The diameter is 0.1, giving a velocity of 15 meters per second. So either the ball is moving 15 meters per second in the air, or the air is flowing over the sphere at 15 meters per second. Putting 15 and squaring it, the force of drag is 0.51 newtons. That is going to be the calculation for a smooth sphere. Let's repeat the calculation for a sphere that's got a surface roughness to it. Here, our value, our coefficient of drag is approximately 0.2. If we put our numbers in again, we see the result is going to be 0.21 newtons. A significant reduction in the drag force seen in this region. Okay, this lecture concludes surface roughness and its effect on force of drag.